All right. We will start now chapter 12, which is media access control, the Mac. As we said before, whenever we are dealing with the broadcast link, we will have two sublayer, the data link control sublayer and the media access control sublayer. And whenever we are dealing with the point-to-point, we will have only one sublayer, which is data link control. Now we will know about random access and control access and channelization. Introduction. Stations are connected, either multicast or broadcast. We need a multi-access protocol to coordinate access to the link. The problem of controlling the access to the medium is similar to the rules of speaking in an assembly. So we need to guarantee some things like is it the right to speak, and no two entities speak at the same time, and do not interrupt each other, do not monopolize the discussion, and so on. So many protocols have been developed in order to do these tasks, and all of them belonging to the sublayer of the media access control, the MAC. Simply, the multi-access access protocols have three types: the random access, the control access, the channelization. In the random access, we will have Aloha, CSMA, CSMA CD, and CSMA CA. In the controlled access, we will have reservation, polling, and token passing. In the channelization, we will have the FDMA, the TDMA, the CDMA. Random access, there is no station, no superior station. And none is assigned to control over another. At each instance, a station that has the data sent uses the procedural defined by the protocol to make a decision on whether or not to send. This decision depends on the state of the medium, either it's busy or and so on. So we have Aloha, CSMA, and these four. Okay, we'll start by Aloha. The earliest it was developed in 1970, designed for the radio. We don't care. Medium is shared between the stations. Okay. Let the station collide and become corrupted. Okay. So here is the concept for Aloha. Simply, each station will send its frame, and here this frame is safe. It will reach safely. But here we have a collision, so all of these are discarded because we are facing a situation where there is more than one frame at the same time, and this is illegal. So we can't have two frames at a time, or we will have a collision. Okay, it should be free, like one at a time. So this will pass, and this frame will pass. The rest of the frames will be discarded because they have collision. Okay, they collide with the other frames and ruin the whole process. Okay. Here it's defining the Aloha protocol. We have the K, which is number of attempts, TP, which is the maximum propagation time, and TFR, which is average transmission time. Here is the TP, which is backup time. It's being calculated using the R, which is here, the random number from 0 to 2K minus 1, and multiplied here by the TB, which is the maximum propagation time, or you can calculate it by R and the TFR, which is average transmission time. And usually the K maximum is normally 15. Okay, it is just a figure to illustrate the concept. Here we have an example to how to calculate the TP. So he gave you the wireless Aloha, a maximum of 16 kilometers. So you have the distance, you have the propagation speed. So in order to calculate the TP, which is the maximum propagation time, you will have the rule, the formula. It's the distance over the speed, which will be 600 kilometers over the 3 multiplied by 10 to the power 8, and you will get 2 milliseconds. And the K, he give you, it's given. Okay, the K is given. It will be 2, so it's given. In order to calculate the R, look at the formula. It's from 0 to 2K minus 1, so it will be 0 to 2 to the power 2, which is 4, so it will be 0, 1, 2, 3. okay, because it's 4 minus 1, so it will be 0, 1, 2, 3. This means that TP, now we want to calculate the back of time, and we say that we can multiply R by the TP, which is the maximum propagation time. We have one maximum propagation time, which is 2, but we have here in the question many R's, so you can choose any one of them if he did not specify it in the question, and you will get different answers. Here it says TP can be 0 or 2 or 4 or 6, because it depends on the one you will choose, the R you will choose from here, okay? If you choose 0, you will get 0. If you choose 1, you will get 2. If you choose 2, you will get 4. If you choose 3, you will get 6, because at the end you will take this R and multiply it by the TP, as you can see here from the formula. Now, the vulnerable time for the normal, the pure Aloha protocol is 2 multiplied by the TFR, which is the average transmission time. So just memorize the formula, the variable time. Here it says, like, if you send data, if B have been sent, so A must start from here, not actually here, and also C. So this could be moved here and this could be moved here, so in order to not make a collision in the B, in the frame of B. So here it says the collision begins, and here it begins. So we want to move the C. So the variable time, which means the time that the frame need to be free. So no other frame must be present in this period except the B. Okay. Example, you have here 200 bit frames and 200 kilobytes per frame. What is the requirement to make this collision free? So how to make collision free? We make sure that it's not within the variable time. So we will simply calculate the transmission, what is called, the average transmission time, uh, by dividing the bits over the kilobits. We will get 1 milliseconds. Then you will multiply it by 2, because the formula says 2 multiplied by the transmission time. You will get 2, which means no station should send later, 1 minute before, and also during its transmission, which is also cost 1 milliseconds. Okay, so whenever I send the B, no one should send anything 1 millisecond before, and also during this 1 millisecond. So the C is interrupting the 1 millisecond for transmitting, and the A is interpreting the 1 millisecond that before sending the frame. So we have one uh, later than 1 millisecond before the station start transmission, and also 1 millisecond during the station while the station is being sent. Okay, so that's what mean by vulnerable time. So the time that should be reserved for that frame to make it error free. The type of Aloha is slotted Aloha, which means still random. So each one sent at a time, but each station sent at a specific time, and also at the beginning of each slot. So if I miss the beginning of a slot, I wait until the next slot. So here, for example, one slot, it will be safe. Here we have a collision. Here we have another collision. Here it's safe, and here it's safe, and here it's safe. So you can say there is less collisions than the normal Aloha. So each frame will be sent at the beginning of the slots, not during the transmission. So as I said, it's still random. Each session will send randomly, but it will wait until the slot begins. So I cannot send something here in the middle. I have to wait until the second slot come, then I will send. Same thing for the third and fourth slot, and so on. So I can send at the beginning only for each slot, not randomly, not totally randomly. Okay. So the variable time now, it's only the transmission time. So there is no 2, okay? There is no second before and the second during the transmission. Only I care about the transmission. So it will be 1 multiplied by TFR, which is only TFR, okay? So this is the variable time. CSMA, which is carrier sense multiple access. So it simply just sends the medium before it try to use it. If it's busy, it won't send anything. If it's not, it will send. CSMA requires that each station first listen to the medium and then check if I shall send or not. Here is just an example. I didn't actually see that this figure. I didn't actually care about it, but it's a really important concept to understand. Here it's just explaining like how there is late in transmitting and some will reach at a late stage. So you can see here, then it's being detected by computer C, then it goes down, then here it's detected by another thing. So here just explaining everything. I actually didn't care about this photo, but it's a really important concept in order to understand the CSMA. It's explained that there is some delay in recognizing or hearing the when the line is busy actually. So this is what the figure describe. Same thing here. So here the important thing is just the variable time equal to the propagation time. So in order for all devices to know that there is the line is busy, uh, it must see the data. So it will reach the station first, then it will reach this. So then it will reach the last one. So the vulnerable time will be the propagation time. So the line declines because there is a late in so there is late in what is it? It will take time to reach for all devices. So there is late, like maybe the first one will know the line is busy in the first second. This line will know in the 5 seconds. This will know after 15 seconds and so on. So variable time equal propagation time to make sure that all the devices sees that the line is busy currently. So variable time equal propagation time. Try to understand it more. Here the behavior of three persistent method. We have three type of persistent methods. First is one persistence, so it will keep continuously sense uh, the transmission medium. Whenever it sees that it's empty, it's not busy, it will transmit the data. Okay, the non-persistence, it will sense, then it will wait, then it will sense, then it will wait, and so on until it sense and find there is nothing, it's not busy, it will transmit. There is the P persistence. It will first start as a continuously sense, then it will check if uh, the R we took it that previously, okay, from 0 to the power k minus 1, okay, less than the P, which is the probability, then sends. Otherwise, waits a time slot, then wait a backup time because it's still busy. Then check again if the R is less than the probability. If so, send. If not, wait a slot of time and so on. So whether it's sent or not sent, it will wait for a slot of time. So here it's busy. It waits for a time. Here it send it, but it's also wait for a time and so on. Uh, so the difference here is just checking the R is less than the probability. Here is the also explaining this in another way. Can skip it. CSMA with the CD, which means with collision detection. So now it can detect the collision. So it has the algorithm to handle the collision. In this method, a station monitors the medium after it sent a frame to see if the transmission was successful. So it will check after sending if the frame has been reached or it got collision or something. If however the collision, the frame is sent again. Okay, so it will check. Here it tells you that the energy should be normal in the medium if there is nothing, but if there were a collision, you will get more energy. So the when he sends, he can identify that there is more energy, so there is maybe a collision or a problem. There is here also a normal transmission. Uh, and here, these three things, there is no energy at all. So whenever we have higher energy, which means we have a collision, normal energy that we are used to, which means everything is fine. And where there is nothing, there will be no energy. Same thing here. Try to understand that it's important. but actually I don't know how to explain, but it says like here sees collision detection and absorption at this point. So here it start to transmit, I guess, then it reach here at this specific time, then it reach here at this time, although there is a collision here with A, and so on. So try to understand this photo. I skipped it actually. Same thing here, try to understand it. Yeah, if you already understand the concept, you won't need this, but this is just to illustrate more, okay? Here is an example. You have CSMA CD has a bandwidth of 10 megabytes per second, which is the standard. If the maximum propagation time is 25.6 microsecond, what is the minimum size of the frame? In order to get the minimum size of the frame, first find the frame transmission time, which is TFR, which is 2 multiplied by TP, another formula. After you get, just double this number, the propagation time, okay? After you double it now, which means that the worst case scenario for the station need to transmit is of period 51.2 microsecond to detect the collision. This is the worst case scenario, okay? In order to get the minimum size, which is the question is asking for, just multiply the bandwidth with the frame transmission time. You will get 5012 bits or 60 bytes, which is also a standard. Maybe these numbers will get changed, but this is a standard number, the 10 and the 64, okay, bytes. Now with the control axis, in control axis, the station consult one another, okay, to which station had the right to send a station unless it has authorized by other stations, okay. We have three types, reservation, polling, and token. In the reservation, simply whoever wants to send data, he sets his value to 1, okay. So here the first one is telling that, oh, I want to reserve something, I want to send something, okay. The rest set to 0, which means they won't send anything. Here there are three reservations, okay, which means 3 of them want to send data, so they will send their data. So whoever wants to send, he will set himself as 1, and the rest who do not want to send, they will set themselves to 0. The polling is designed as a primary station, so whenever the primary device controls the links, the secondary device follows its instruction to determine which device is allowed to. So there is a primary device that control the flow of the things. So here it says there's two methods, the select and the poll. And the select, the primary device select the device that can send now. The device bring the acknowledgement. Then the primary will send him a data. Okay, then the receiver will give him acknowledgement to say that I have received the data. This is the select method, which the primary station selects the device to send him a data. Whereas in the polling, it will poll the first device. Polling is just like asking him, do you have data that you want to send? The station say in acknowledgement, which means the negative of the normal acknowledgement, which means it's has nothing to send. Then it will poll, or you can say ask the second station, do you have something that you want to send? Or it says yes, so it will immediately send the data, and the primary station will acknowledge him, which means that, oh, I have received your data, okay? The token passing, uh, it's like a token circuits. The one who have the token send the data. When the data finish sending all its data, it will pass the token. So it will hold the token and send its data. Once it finish or there is no more data, it will just pass it will release the token or just pass it to the next logical station in the ring. Okay. So here we mean by logical and physical. The physical that we see it in action or we see it in the real life. The logical is the way that it's the operations have it at the back end, so you can see it. So all of them have the ring as the logical concept. Okay, but they differ in the physical parts. So Here we see it as a dual, which means two rings, but they are reversed for each other. Here it's the star topology. You will see it in physical as a star. So you will see it in real life as a star, but logically it's as a ring. Here, physically, you will see it as a bus, but logically all of them are ring, okay? Now channelization, channelization or channel participation. So it will make available a bandwidth of link is shared, time, frequency, or through code among different station. In the section with FDMA, we have three type. Okay, FDMA bandwidth is divided into frequency bands. So each station is allocated a band. In other words, each band is reserved for a specific station, and it belongs to a station all the time. Okay, so here is an example. Okay, so here each one of them will take a small portion from the medium. So the first one will take this small portion from the common medium. This will take this part, second part. This will take the third part, and the last will take the fourth part. So it's shared in order of the frequency. So each one of them will take small portion of the frequency, and then it will be summed all in the common channel and will send together. Okay, but each one of them will take small portion each time. Okay, the other type is TDMA. It will allocate the, what was it? Each station is assigned to a time slot. So each station will own the whole common channel for a specific amount, the specific time period. So each one of them will use the whole, as you can see, the whole medium for a specific amount of time. So this time for this station, this time for the station, and so on. Okay. He will use all the resources of the common channel for a specific amount of time. Okay. This is the TDMA. Time division multiple access. The CDMA, which is the code, combines the two concepts together in order to make it more efficient. So it differs from this, that only one channel occupies the entire bandwidth, and also there is no time sharing. So all of them have have the whole time and the whole channel. Okay. So the concept of it like this. Uh, the common channel will be like a formula. The D1, which is the data, with the C1, which is Walsh table, I guess, yes, and D1, C1 multiply, then plus D3, C3, and D4, C4. We will know more about them soon, but currently you will receive the data, then you will multiply it by something, you will get it from something called Walsh table, and same for every data of them, okay? Then they will be common. So all of them will use the whole frequency, the whole bandwidth, and also there is no time sharing. So all of them, the channel will be common up for all of them, and they can use the whole resource, the whole frequency and time of it. Okay, so it combines the concept, or it's combine the concept of the FDMA and TDMA and make it much better. Okay, so now let's discuss this. The C. The D will be the data it will be given. The C you will create it yourself. Let's explain the concept of the Walsh table. Uh, Simply, you will start by a normal, it will be +1 or -1, doesn't matter, or sometimes it's mentioned in the question. So after you decide this, you will open, uh, you will try to make it bigger, and you will keep it constant for the three parts, but you will change it. You will get the complement of it in the fourth partition. Okay, so here is an example. After starting from 1, you will make it bigger. 1 the same, it does not change, the same here and here and here. Okay, then you will negate it. You will negate it, you will get -1. Now this is the second Walsh table. Assume I want to get the third Walsh table, which is the fourth Walsh table, because it's always multiple of 2. Okay, uh, I want to get the fourth Walsh table. I will take the whole one of this, and I will consider it as one of this. So you will take it the same here, the same here, the same here. Now in the third part, you will negate it. You will negate it. So you will change every sign of each one. So here it's +1, +1, +1, -1. You will make it -1, -1, -1, -1, +1. So this is voltage table 4, and this is voltage table 2. I hope it's clear. And it should always be multiple of 2, okay? As we will see in this part 2, there is more details in it. Then how this is how we extract the C's that we saw it here, okay? You will take the first line of the wash table, second line of the wash table, third line of the wash table, fourth line. So first line, plus 1, plus 1, plus 1, plus 1. Let's see, plus 1, plus 1, plus 1, plus 1. Second line will be plus 1, minus 1, plus 1, minus 1. Let's see, plus 1, minus 1, plus 1, minus 1, and so on for the rest of the wash table. Here we have 4 stations. We will have 4 C's, C2, C3, C4, okay? Now, it says a common convention in the representation in the CDMA, which means the data. We will receive the data, the D1, like this. We will receive it as 0, we will receive it as 1, or we will receive it silence, nothing. So whenever we are solving the CDMA problem, we will convert the 0 to minus 1, we will convert the 1 to 1, we will convert the silence to 0. That's why we make this in order to make the silence has a meaning. So if we do not make the silence has 0, we won't able to multiply here, okay? So, and 0 we make it as minus 1, and 1 we make it as 1. It will be more clear with an example, okay? There is some mistakes in this example, as I remember. This should be minus 3 at the end, but just ignore the example. It has many mistake things, but just take the concept. Okay, so you will get this bit 0. It will be given, and as I said, as I said before, when I get bit 0, I will convert it to minus 1. So here it is. I convert it to minus 1. This is the D. Okay, the D that we have taken here previously. This is the D. Okay, the D. Okay, we'll have the D as minus 1. Now, from the wash table, we got this C1. Okay, from here, plus 1, plus 1, plus 1, plus 1. From here, we got the first line. So here, plus 1, plus 1, plus 1, plus 1. What you will do now, you will multiply the D by the C, and then you will get this. Minus 1, minus 1, minus 1, minus 1. Okay, this is for the first station. Same for the other station. Here it says silent. So what are you going to do? Silent, convert it to 0. You will convert it to 0. Now you have the D. And the C3, we already get it from the wash table, the third line of the wash table. Plus 1, plus 1, minus 1, minus 1. Okay, you will multiply 0 by this. We will get, of course, 0 at the end. We got the thing for the station 3. Same, when you have a bit as 1, you will make it plus 1. So now it's plus 1. This is the D. And the C4, you already got it from the wash table, the fourth line, plus 1, minus 1, minus 1, plus 1. You will take this one and multiply it by this. You will get the same thing. Okay, and at the end you will sum all of them. You will sum this with this with this with this, and at the end you will get, I guess, minus 1, minus 3, minus 3 plus 1. Okay, in the comment channel. So we are applying this formula at the end. We are applying this formula. Okay, multiplying each data with its corresponding wash table line, and then sum it at the end. Okay, and then sum it at the end. So we know how to convert this to its appropriate number. We see how to get this from the wash table. We'll multiply each of them to get the D and the C, and at the end we will sum them all in the comment channel. Here just digital signal representation. It shows you, like, when you have minus 1, it goes down. When you have 0, silence, you have nothing. When you have minus 1, it goes up as a block, 1 block up. When it's minus 1 block down, when it's minus 1 block down, and so on. Here is also down minus. Here is also minus, minus, and then minus 3, so it should be bigger block, and so on. So if he asks you to do the digital signal representation for this, you will do it like this blocks. Okay, same thing here, but here he's telling you that you can get the original data from the given given what. This is the number of stations, but the minus 4 for what? I forget it. But the concept is that if you divide the original, there's also here mistakes also, I guess, in the and the calculations or something, but just get the concept. Whenever you take the original C, the C2 or the C1 or etc., and you multiply it by the common channel, the final result that you get, you will get the total number of station that you have. In this case, it's 4, so you will have -4. Okay, it's either minus or plus. Okay, doesn't matter. Just take it as it is. Then divide it by the number of station. We have 4 station. How did you know? Either you count this numbers 1, 2, 3. Okay. Either you count this number or it's given the question, oh, you have 4 stations, or you can see it from the figure, oh, I have 4 stations. So at the end, I will divide it by 4. So when you ever divide the common channel result that you have, which is in the middle, with any one of these, the C2, the C4, or the C3, and so on, you will get the number of station. So you will divide it by the number of station that you have, which is 4 or any other thing. Then you will get this 0 or this 1, okay, or the -1, but it's not the data, the original data. So you will convert it as we saw here, but in reverse. Okay, so you have bit -1, make it as 0. So this is the bit that you have. If you get -1, then convert it to 0, you have this bit 0. If it's 0, so it's silence, and so on. So in this example, he picked one of them and multiply it by the common one that we got after summing all of them. Then he got the number of stations with the minus. Of course, keep the minus, of course, don't remove it, and then divide it by the number of stations, which is in this case 4, and then you will get -1. Is this the final data? No. You will convert it. The -1 will be converted to 0. Then the bit 0 is the data, the original data that you have. Okay, the original data that you have. Okay. Here is explaining more about the wash table. Find the chips for the network 2 station and 4 station. So you will get it this way. Either you start from +1 or -1. They will give 2 different wash tables, but all of them are correct, depending on the question. If he didn't mention, pick any one of them. So after you give this one +1, okay, here the example he starts with the +1, so you will keep the 3 parts the same. Then you will negate the last part, and so on for the rest. Then you will take the whole wash table, also make it the same in the 3 parts, and then negate it in the last part. We can use for the 2 station network we have. Yes, here it's telling you that when you have for example 2 stations, this wash table is enough. So this will be C1, this will be C2. This when we have 2 stations. What if we have 4 stations? What if we have 4 stations? We want for the wash table of 8, because we want 4 C's, not 2 C's. So we will have this as C1, this as C2, this as C3, this as C4. Okay, C4, C3, C2, C1. Okay, so we will have this C1, C2, C3, C4. This is when we have 4 stations. So if he asks about for 2 station, you will do this. If he asks about 4 station, you will do this, and so on. You will keep going whenever he asks a question. So now he gives you a question. Assume that the number of sequences that you want is 90 stations. So I want 90 station. Is there a multiple of 2 that you have to? Is there any multiple of 2 that you have to make an accurate wash table with the equal number of 90 C's, which mean lines? Okay, there is no. So you will pick the biggest one above the 90. So here, 2 to the power 2 to the power 7 is the correct answer, which is the 128. So with 128 lines, okay, we can have 90 sequence of chips, which means the C's. Okay, we can have the C's. What if I picked 2 to the power 6? It will be 64, which is not covering the whole 90. So you must go for the bigger option, which is 128. You will use only 90 of them. So that's mean there is 128 minus 90. Minus 90, you will have 38. So 38 C's or chips are not used, but it's okay. So the most important thing that we are covering the 90, and as always, it should be a multiple of 2. Okay. Here is an example that explains the concept that we have got. We have shared here, like how to get the data. So we have a rule that says if I give you all the common channel and I ask you to get the data of one of them, just multiply the original C with all of them. There is a properties that the C, when it's multiplied by different other C's, it will give 0. So you can see that here we got 0, 0, 0. But when it's multiplied with its own with it, when it's multiplied by itself, it will give the number of stations. So here we have the data, the same data here, and the number of stations. So at the end, you will have the same as here. We will have the -4, okay? But you need to divide it by n, which is the number of stations. Then you will have at the end the data, the original data that you have, and don't forget to convert it to its original bit, okay? Its original bit. So when we divide the result by n, we will get the D1. Okay, I hope it's clear. It will be more clear with the part 2. I guess it's the same thing, but there is maybe some notes. I don't remember actually. Let me see. Let me see. 12 part 2. Let me check this very quickly. So nothing new till here. The new thing starts from here. Okay. This is the property that I was trying to explain when dealing with the C's. Okay. It's here. It's just normal. When you multiply anything by it, it will be normally multiplied. But if you multiply it by itself, it will give you the number of stations that you have, which is 4 in this case. When you multiply it by any other one that it's not the same, it will give you 0. It's a property. So if I multiply this by this, or this, or this, all of them will give me 0. But if I multiply the C4 by itself, also C4, it will give me the number of stations. The normal addition, of course, will give you normal addition. So this is normal. Think normal case. Multiplying is the normal case. This is normal case. Here it tells you if you multiply any two different C's, you will get 0. So it's a property. And whenever you multiply the C by itself, you will get the number of stations that you have. Here, as we said, that's how to convert. If you have zeros, you will convert to -1. If you have 1, you will make it +1. And when you have silence, you will make it 0. We took this already, and as I said, this is a mistake. It should be -3 here. The concept, I hope it's clear. Converting the 1 to the +1, the silence to 0, and -1, 0 to -1. Then multiply it by the C that you get from the Walsh table. Then at the end, sum of all of them. Sum this with this, with this, with this. You will get this in the middle. The digital signal, we saw it already. This we saw it already. Here it's explaining that it should be 2 to the power m. So you will have 1, then 4, then 2, then 8, and so on. You will keep just going by to the power of 2. We took this example and also this example. Yeah, that's it. That's it for this chapter. This is very important, and I guess it's the same concept as here. Okay, same concept. Whenever, as we said in the property, whenever you multiply 1 by itself, it will give you the number of stations. Whenever you multiply it by the different stations, you will get 0. So all of the data that we don't want will be disappeared automatically. At the end, we will have the number of stations multiplied by the data. We want the data, so we will divide by the number of stations. We will get the data at the end. That's it for chapter 12.